Good afternoon, everyone. My name is Gao Feiyuan. I'm from Dalian University of Technology. I'm honored to speak at this conference. Today, my topic is about internal and combination resonance of a wind top blade with coupled flapwise and endwise bending. I want to share our interesting research results with you. The content of this presentation is divided into 5 parts. In section 1, I will introduce my motivations with you. In section 2, I will give an aerodynamic model of a windtop blade. Then the model will be solved through the math of multiple scalars in section 3, and the numerical solutions will be solved in section 4. Finally, I will make a conclusion. Well, let's move on the first part of this topic. As shown in picture 1, global cumulative installed capacity increases year by year. The blade size of the windtop become larger, which makes the nonlinear vibration analysis of the blade particularly important. Due to the complex aerodynamic and structural characteristics of windtops, it's difficult to analyze the nonlinear vibration of windtop blade. Before building a theoretical model, I will introduce my basic assumption and theories. First, the torsional rigidity of the blade is assumed high enough so that the twisting of the blade can be ignored. Besides, the axial dynamic deformation of the blade is negligible compared with the structure due to the centrifugal force generated by the rotation, and the fluid domain is decoupled from the solid domain. The interaction between the structure model and the aerodynamic model is shown in the figure. In this paper, IR conditions occurred in the free oscillations of multiple degrees of the freedom systems, which existed positive or negative MI such that the equation is satisfied. PR is the resonance of a mode triggered by the external excitation. CR is combination of the IR and PR, and NR has non-condition of frequencies. The occurrence of IR is caused by the model nonlinear coupling. So how to deal with the nonlinear terms in governing equations will become the key point of this paper. First, Lagrange strings lead to the nonlinearity of this paper, which is represented by the tensile force in the governing equations. Further, the nonlinearity will be assumed to the governing equations of modes and multiscalar equations. Take CR between 3 flapwise modes and an endwise mode as an example. Its frequency need to meet following conditions. Epsilon sigma 1 and epsilon sigma 2 are the determining parameters to describe the proximity of IR and PR frequencies respectively. Let's move to the theoretical model of our research. First, the structural model of a blade is established as shown in figure. I used 4 coordinates to describe the motion of the blade. Aerodynamic force and moment under the action of wind shear are modeled as follows, where lambda represents the inflow velocity ratio, and it represents the angle between the blade speed and the inflow velocity, which is an important aerodynamic parameter. By combination the aerodynamic model and the structural model, the aerodynamic governing equations are obtained as shown below. Then the Galerkin means and assumed mode means are used to describe the governing equations, and the governing equations of the blade are obtained as follows. In these equations, except for an autonomous term AK, all other terms are changed with time. I adopt the method of displacement separation to eliminate the autonomous terms. First of all, the displacement Q is decoupled into the dynamic displacement Qd and the static displacement Qs. Then they are substituted into the governing equation to obtain an autonomous equations only related to the static displacement. At this time, due to the action of nonlinear terms, stiffness coupling terms will be general, and I use the mass of eigenvalues transformation to eliminate these coupling terms. Finally, multiscalar transformations is used to solve multiscalar equations in varied cases. The transient responses under NR and IR are shown below. Tk1 are the coefficients of nonlinear terms which can be used to represent the strength degree of geometric nonlinearity. The transient and steady state responses under PR and CR are shown below. T46 is different from the other coefficients. It represents the strength degree of aerodynamic force. Before showing the result of calculations, I validate the linear frequencies of this paper. It can be seen that linear frequencies are in good agreement with the existing results. In the next two pictures, we can find the theoretical spin and the inflow velocity ratio correspond to the three resonors. Here, we illustrated the transient response under NR. Alpha 1, alpha 2, and alpha 4 are synchronous and pi out of phase against alpha 3, which means their existing exchange in energy from the first Flapwise, second Flapwise, and the first Edgewise mode to the third Flapwise mode, and vice versa. As for the transient responses of CR, different from the amplitude response curve of IR, the transient response of CR contains two main frequency components, which are caused by IR and PR respectively. After the transient response, the vibration will enter the steady state. I study the influence of aerodynamic force and damping on PR, as shown in these two figures. There is an unstable range between jump point A and jump point B. Amplitude alpha 4 and the unstable range rise as aerodynamic force increases and damping decreasing. The influence of aerodynamic force and damping on CR are the same as that on PR. Combining steady-state responses of PR with CR, alpha 4 on CR is smaller than it under PR, since its modal energy is transformed to other three modes. When the aerodynamic force is down to a smaller value, the subtle, narrow, unstable range in PR disappeared from CR due to the redistribution of modal energy. Pick a point in the unstable diamond and change bit B. We can also see the phenomenon of unstable range disappearance. As for the effect of geometric nonlinearity on PR and CR, different from aerodynamic force and damping, geometric nonlinearity has little effect on the maximum of alpha 4 under PR. From the steady state responses under PR, we know that the maximum of alpha 4 is only affected by aerodynamic force, frequencies, and damping. And an enhancing geometric nonlinearity reduces the maximum of alpha 4, but increases the maximum values of alpha 1, alpha 2, and alpha 3, since internal resonance is strongest. Changing lambda 0, beta p, and epsilon sigma 2, the steady state responses are in these two figures. In first Flapwise, we can see different from the red and green curves. The maximum of black curve increase at first and then decrease as the lambda zero increase, which is because aerodynamic force can increase with increasing lambda zero, but damping is opposite. To sum up, first, internal resonance, primary resonance, and combination resonance are analyzed through the math of multiple scalars. Consider the first three Flapwise modes and the first Edgewise mode. Second, influence of primary resonance and internal resonance on the frequencies of the transient responses under combination resonance are demonstrated. Third, influence of combination resonance on primary resonance for steady-state amplitudes and their stability is discussed with different parameters of aerodynamic force, damping, and geometric nonlinearity. Final, parametric analyses are present to show how steady-state response of Flapwise and Edgewise modes vary with determining parameters and designing parameters. That's all. Thank you. Are there any questions?